Yes, and a lot of assignments also. A lot of subjects, all the subjects.
Oh, okay. So I posted the second assignment also. Don't worry about the deadline. The only way. So I think when our quiz is on the 10th, right?
Yes, sir. It's on 10th.
Yeah. Okay. So that's we'll have quiz until the topics which I mentioned in assignment one and assignment two. And assignment two is largely to just give you a little feel of what kind of problems to expect, and then also to get you some practice on these things, on the kind of problems to expect, kind of problems to expect in the quiz. So I think that is kind of okay. So any other questions you have before we start?
So, sir, as far as lectures are concerned, from the lecture perspective, the course is up to the last lecture what we had we have covered, or like is it something before that?
Uh, for the quiz?
Yes, sir. For the 10th November quiz.
Yeah. Until what we did until last Monday.
Yeah, last Monday, right? Okay.
Yeah. That's okay, right? I don't want to like maybe I'll just start a bit of
Yes, absolutely.
Yeah, or if you want to drop half a topic or something, then we can still like do that.
I'm
Okay,
okay with that. I don't know about
no,
others.
it should not be like after you drop, everybody proposes one topic and at the end we are left with nothing. So anyway, so I think what you could do is to look at the problems that that are in the assignments. Maybe on Wednesday, if that is okay, we can talk a little bit about those problems while we meet. I'll just check what the time slots are. What is the free time slot on Wednesday? If at all.
Usually we do have a TSA session on Wednesday, but I think we can shift that to Tuesday evening. If possible. I'll talk with Anish sir on that, but like usually it is packed for both the lectures. So from 4 to 5:30 we have this TSA session, and then from 5:30 to 7 we have multivariate class. Yes.
And Thursday is free, or how is Thursday?
Thursday also we have a Python class like after the regular lecture of TSA, but definitely what we can do is for this week, since we have our midsem, we can ask Anish sir to basically postpone or reschedule that. One of the things, either on Wednesday or on Thursday. That is I think so.
Multivariate class is there tomorrow?
Tomorrow it is not there. Tomorrow I think
Today
we have yes.
Today's second class is the multivariate class.
Okay, then let's not touch that. I just met Jay.
Tomorrow we have a slot, right, Anchal?
Yeah, tomorrow we have
slot is there.
Yeah, correct.
Tomorrow it's available, sir.
But tomorrow it would be early, right? Because people would not have done the second assignment.
Yeah, just check the assignments and then and give me a time slot, and I will be available.
Sure, sir, sure. We will discuss with the TSA faculty, and we'll let you know, sir. Either it will be on Wednesday or Thursday. Yeah, sure.
Sure, no problem. Okay, so
one point, sir.
Yes, sir.
So I would like to request the keywords for the like what are the syllabus is there for like midterm.
Okay.
So can like the list of keywords can be given?
Okay, no, that is I won't give that now. Just look at the assignments. No, otherwise what will happen is if I give 5 keywords, okay, I would have forgotten the 6th. So you will go to the index of the page and then look at say rank, and you look at nullity. Then I would not mention column space. Then you would not, So let's try to solve the problems in the assignment, and those are the keywords, right? And I think largely whatever we will cover will come through that. I think that is a better way of doing this than just me giving keywords, because I might forget something.
Okay.
So just have a look at the assignment problems today, tomorrow, Wednesday, and maybe we can meet Thursday or something like that, or whenever, whatever is a is a convenient day and time for you. Okay,
Yeah,
so
sure. Thank
a little bit of introduction, and I'll start motivating with a problem and see kind of where we will end on this, right? So, okay, some kind of. So let's say I have this problem where I am planning. The screen is visible, right?
Yes.
Okay, good. So I am in this situation where I'm planning a school trip for 400 students, and then I don't have so many buses, so I'll hire a transport company. Of course, nothing is linear in life, so this transport company will have 10 buses of 50 capacity, and then 8 buses of 40 capacity. Okay. So what we want to look at is we want to minimize the total cost of the buses. So this bus per trip would cost say 800 rupees, and say the smaller bus would cost 600 rupees. Okay, so we want to minimize the total cost and with the constraint that, okay, I have this is my constraint. I want to transport 400 people, and I only have 9 drivers. Okay, so this is this. Okay, so I have to transport 400 people. If I had 10 drivers, maybe the thing would have been easier. But I have a constraint that, okay, maybe one of the driver didn't show up, so I only have 9 drivers. So how will we solve this problem? And the reason I'm also saying of how will we solve this problem is largely much of our theory will be set around how we formulate this problem, right? So the idea is to first, before just giving some random, you say, okay, let me do 5 of this and 4 of that, do some kind of a nice mix and match, see what works. Like we typically solve that Rubik's cube, right? Where we just arbitrarily try some moves and see if it works or not. But largely, okay, we do not want to do it, in that way, right? So, okay, so the idea is to how will we write this mathematically? Okay, so the first is, okay, what do I want to do? I want to minimize my cost, right? So what is my cost? Cost per bus, one bus is at 800, other bus is at 600. So the total cost would be, say, suppose I have X number of X number of 800, X number of the bus A and Y number of bus B. Okay, so this will be my cost, right? I have to pay 800 for one bus, other bus for 600, and I want to minimize this cost. Okay, now if I want to minimize the cost, I will maybe just do something arbitrarily without any constraint. If I say I want to maximize all my, so we just would have got salary last week, and I want to say I want to maximize my savings. What would the algorithm suggest? So say I get, say, whatever, say $2,000 of salary, or say 2 lakh rupees of salary. So if I want to maximize my savings, what would anybody suggest? So first would be to just save everything, right? Save or invest or whatever. But then it will come with things that, okay, I have to pay my possibly house rent, I have to pay my electricity bill, I have to pay my water bill, I have to pay, I don't know, my children's school fees, and so on and so forth. And based on that, then you kind of see how much can you save, how much you can optimize. You maybe watch only one movie instead of two, or there is a Diwali weekend, so you want to spend money and so on. So this minimization of the cost also comes with some additional constraints, right? So and how will you write those constraints mathematically? So first is how to incorporate these constraints, right, of 9 drivers. So how many number of buses I have? The total number of buses I have is x plus y, right? X of 800 or the 50-seater capacity, y of the 40-seater capacity, which cost 800 and 600 respectively. So x and y, so x plus y, I don't need to employ all the drivers, right? It can be less than or equal to 9. Okay, this is the constraint on the driver. So I have taken care of this. Then what is the other constraint? Other constraint is I have to transport 400 students. Okay, which means how do I write that? So one bus can carry 40 students, other bus can carry 50 students. So this will be 40x plus 50y should be at least 400. The drivers was at most 9 and the students should be at least 400. I cannot have 397 and ask 300 to drop out because I will save 1,000 rupees. Okay, that is not allowed.
Sir, it
Sir,
would
is
be
it 50x plus
50x
40y?
40i.
Okay. It is 50x plus 40y is greater than or equal to 400. I need to carry at least 400, right? Or all the 400. Okay. And it's okay that if some buses have seats free. In addition, okay, the number of buses is always greater than or equal to 0. Okay. Now I have so my cost will be, say, if I take 5 of these buses, my cost will be 4,000 plus 3,000 would be 7,000. And will that take care of my capacity? 5 of these buses will take 250. 5 of these buses will take 200. Okay, but then I do not have so many drivers and so on. So how will I solve this, right? So I want to minimize this number. Okay, so if I just look at what we will define as the feasible region. What is the feasible region? If I call this as X, if I call this as Y, I'm only allowed to go in this direction, right? So X is greater than or equal to 0, Y is greater than or equal to 0. Okay, and then X plus Y is less than or equal to 9. So suppose, okay, this is the point X plus Y equal to 9. Then I have a region which is like this, right? And typically now I'm looking at this, all this here, X plus Y will be less than or equal to 9. Similarly, if I look at this constraint, 50x plus 40y is 400. So if x equal to 0, y is equal to 10. And then if y equal to 0, x is y equal to 0, x is somewhere here, 8. This is 10, this is 8. I'll use another color, this is the green one. Okay. Now this will be the region, right? And the constraint is this must be 50x plus 40y is greater than or equal to 400. This green line is the equality line where 50x plus 40y is equal to 400. And now I am looking at the region where, assuming I'm drawing it correct, something like this, right? So what is my region here, right? So all this constraint 1 is satisfied. So say suppose if I'm just looking at points, right? If I say will this point satisfy these constraints, Will a point here satisfy this constraint? Will a point here satisfy this constraint? For example, if I take this point, this will satisfy my constraint that 50x plus 40y is greater than 400, but this will not satisfy x plus y is less than, this will be x plus y is greater than or equal to 9. Similarly here, right? So the only region is the intersection of these four regions. That is essentially like I'm looking at the region which is here. These are, whatever is now this dark green region, these are the feasible region which have the allowable values of x and y. Okay, now within this region, I can now search for what is a good x, what is a y. Of course, you may say, sir, there are infinite points in this. Of course, I will not also have 1.1 buses or 6.2 buses. So the search set is a little smaller. But what we will see later is it turns out the following way, right? So I can compute the cost here. I can compute the cost here and the cost here. Okay, let me call this the cost 1.
Sir, one
cost
more
2.
constraint will be there on y.
Which one?
That sir, one more constraint on y will be there, that y cannot be greater than 8, means y should be less than 8. And on x also, like 10
that is
buses only we have.
sure. I think that is taken care of somewhere here. I think that should be okay.
Which one?
That okay, you want that x is greater than or equal to 0, but x is also less than or equal to 10.
Yeah, and y is
Yeah,
less
okay.
than.
That is fine. So I think I will have somewhere this is x should be 10 is somewhere here, and y should be 8. That will be maybe somewhere here. That's okay. I think I'm that's a little larger region also. And I think when I do these two, I think they should be kind of taken care of, because whatever happens will be now inside this only. But yeah, I think that's redundant, but you can still write down that as a constraint. Okay. Okay. So I'm looking at what are the allowable values of x and y. Now I don't, and then within the allowable region, I just find what are the allowable regions of x and y, and within so this region I'll call the feasible region, which has set of all x and y. We find the x and y that will minimize 800x plus 600y. Of course, there are a lot of things here, but what we will show later is that if I just take these 3 points in red and I say cost 1, cost 2, cost 3, I do all these things, all these 3 things, and I choose the minimum of C1, C2, C3 will be my optimal cost. Okay, we'll try to argue why this is true. For now, I think the feasible region thing is clear. And then I don't need to search for all points here or along all points inside or on the boundary of the triangles. I only will search at this intersection points of the constraints. Okay, so this we will call it later as a linear program. Now we would have heard it somewhere. If not, that's okay. We will still learn it. Okay, this is fine. Okay, if not, then we'll move on to something else also. Yes, sir.
Sir, these C1, C2, C3, these are the coordinates, right? The 3 coordinates that
No,
red
this is
highlighted.
okay. C1 is the cost. Is a cost at point 1, cost at point 2, and cost at point 3. So each one will have a x1, y1, right? This will have a x1, y1. This will have a x2, y2. This will have a x3, y3. So based on this x1, y1, I will get a cost. Based on x2, y2, I'll get another cost. And based on x3, y3, I'll get another cost. I just compare those 3. I just choose the minimum.
Okay, good.
Okay. And then you may argue, what if there are, like, say, there are a lot of constraints and maybe there are, say, 25 of them. Do we really have to compute 25? That is what some efficient computational methods is also what we will look at. Okay, so that is one motivation. And the second one, which we will also look at. Yeah, there's a question.
Yeah, yes, sir. How about points in the area of the triangle, which were in the center of the triangle? So that cost will be higher than C1,
Hi.
C2, C3.
This will definitely be higher than C1, C2. We'll actually prove all those things.
Okay.
So this is just a little introduction to what will come up later. But you can safely assume for now that the cost will be one of these 3 points will be the best cost. Point number 1, point number 2, and point number 3. Okay, good. So I'll go to something else. I'll stop sharing for a while and then get to a new file. Just a second. Okay, so the other set of problems that we will encounter through this course is, okay, we start with, so largely we would be interested in minimizing a function. So, or maximizing it. We could also cast the problems as either a minimum or a maximum problem. Minimize a function, where in that case it was the cost, but that was not very easy, because I could just say, look, don't transport anybody, everybody is at home, I don't need to spend anybody, and therefore I minimize the cost. But then that is not usually the most smart solution, right? Because you want to transport 400 people across several buses. Okay, so what if, so x equal to 0, y equal to 0 is the minimum when there are no constraints. Okay, and suppose I as a very simple example, just say I have a function y equal to 2x square. Okay, what is the minimum of this function? Without knowing any calculus also, I think we can we should be able to tell this. What is the minimum of this function? Is 0.
0.
Okay. Now, yeah. So suppose I say, okay, this is the minimum is 0. But what if I say y equal to 2x square, such that x is between -1 and +1? What could be the answer?
0.
0?
Yeah.
2? I think that because x equal to 0. So what if I say that x is greater than or equal to 1? So I have
1.
y equal to twice x
2.
square, greater than or equal to 1. I have here, this is my point. And then now at x equal to 1, y will be 1. Okay. Now this is, things are, okay, what this, the first thing solves is something called an unconstrained optimization program. Okay. And then when I add things like this becomes a constraint problem. Okay, now this is a nice kind of function, so I can say a lot of these things just by visualization, or slightly complex functions I can say maybe with the help of some calculus here and there. Okay, so in general, I will have an objective function to be minimized such that f is of, say, n variables, could be, say, not just y equal to x square, but I can have y, which is a function of, say, x1 till xn, as, say, x1 square plus x2 square all the way till xn square. or in general any other function. So y could be, I don't know, the cos of x1 plus log of x2 plus x3 and so on and so forth. Okay, so it could be arbitrarily any function of x1 till xn. Okay, so and then the idea would be to minimize the value of this function. Okay, so this is fine. So okay, we'll go to this. Suppose my function looks like this. Okay, and then I were to search a minimum, right? So what I will do is, okay, so this, if I just look at the function within this range, and I can say, well, I have a smaller, this is the minimum here. But if I look at something here, or maybe within this, I said this is the minimum, right? Whereas the function here will have several minima. So we have to classify between what is a local minima and what is a global minima. Okay. So that will be the premise of this. So we just read out something, right? So so when I do curve fitting is essentially, what do I do? If I okay, sorry. So the problem that we had started off with, and we'll again revisit this today, is if I had a point 0,6, then I had a point 1,0, and then I had a point 2,0. Then I'm looking at what is the straight line that passes through these three things. And then we had solved the minimization problem that I wanted to minimize the square of the errors. Okay. Same thing I could do even if I could fit a curve, right? Okay, it actually turned out to be quite beautiful that we could easily fit a curve. So the objective here is that there will be, of course, the error between the actual value and the predicted value, and what I want to minimize is the square of the errors, or the square of the residues. Okay, we will formalize that a little bit. Okay, so what is a minimization problem, right? Especially when we are dealing with generic problems. So x is a global minimizer. So if it covers all of xn, that the value of f at x is less than or equal to the value of f of x at all other points. Okay, it is a local minimizer if there exists a neighborhood containing x star such that, so for example here, this is sorry. Okay, so here, if this is my x star, okay, and if I take a little neighborhood here, then this will be my minimum, right? So so that is the definition of a local minimizer. Strict global minimizer would be that f of x star is less than. So here I can give maybe an example like this. So the two things I have is I have a function which is like this. Okay, so at all these points, which is in the thick line, f of x star is less than or equal to f of x. Okay, and then the strict global minimizer would be that at x star I am less than all other points. So here the x star is something kind of a set, but on the other example of the parabola that we saw, that except x equal to 0, all other points, so f at 0 is strictly less than f at all other points. Okay, so now this is the difference between global and local minima, and then this is how we will define it. Strict global local minimizers, strict global, and strict local minimizers. Okay. Okay, so given a function f of say several variables, let's say I have f of x1, x2 is say x1 square plus x2 square, say divided by 2, the gradient of f, the gradient vector would be d of f, the partial of f with x1, partial of f with x2. In this particular case, it will just be x1 and x2. Okay, geometrically, it means that, okay, if I'm at x1 square plus x2 square, I'm looking at a level set which is like this. The gradient will just give me vectors which is go outside, radially outside this circle. Okay, and now Taylor series expansion tells me that if f is differentiable, then then I can write this as a first order approximation, and I can also write down the second order approximation. I'll not do much of this thing, but we'll just learn it the way we need. Okay. Now, a necessary first order condition for a local minimum is that f is continually differentiable, and then we look at the first derivative, df by dx going to 0. Right. This is what we look at all the time. Again, this is the reason I say that this is necessary but not sufficient is because if I look at a curve, like a sine curve, right? Say I start from here. So at this point also df by dx is 0. At this point also df by dx equal to 0. But here it is the max, here it is the minimum. And therefore now we look at the second order conditions also for to get the minimum. Okay, so I'll not do the proof of this, and then the second order condition to check whether it is a maxima or minima is we look at the Hessian condition. Again, I take the same problem of half x1 square plus x2 square. The gradient will be is x1, x2, and the point at which the gradient goes to 0 is both x1 star and x2 star are 0. The Hessian will be, again, I'm looking at this, so I'll have a 1, a 0, a 0, a 1. So I'll just write a general formula for computing. So given f of x1, x2, the gradient of f is the partial of f with x1, the partial of f with x2. The Hessian of f will be the double partial of f with x1. Here it will be the double partial of f with x2, and so on. So here I'll have d to f by d. So I have these two functions of it, so okay. And then d to f by d. So I'm just looking at the second derivative of this. So I'm the first component here. I take its derivative. Okay, sorry, I think I should write it a little better. So the Hessian of f is d over dx1 of the first component here in the gradient of f. The first component in the gradient of f is df by dx1, and then the second component df by dx1 of the second component. Similarly, d over dx2 of the second component, and then d over dx2 of the second component. So in this case, the partial with x1 of the first component is 1, 0, 0, 1. So this is greater than or equal to 0. Then we call x to be x star, which is 0, 0, a local minimizer. Okay, so this is the general geometric interpretation of what is the Hessian. Okay, I'll come back to set of convex functions, but today we'll start off some of the basic methods to solve problems of this kind, and we will call this as the gradient descent method. I think you would have heard of this in some machine learning class so far. Okay, so we'll quickly check what this gradient descent method does for us. So what we are looking here is to solve an unconstrained optimization problem of the form that I want to minimize over x, f of x, where x is just some element in Rn. Okay, so we now know the concept of local and a global minimum. Okay, so typically we may argue that, okay, given f of x as a function, I want to minimize this. I would compute gradient of f of x, set it to 0, compute x star, and then compute the Hessian and check if it is greater than or equal to 0. In many cases, it may happen that, again, here I'm solving an equation, right? So this means I'm solving possibly nonlinear equation.
Sir?
Yeah.
Sir, the second differential, double differential is there, na, sir? Second order. So what does it
Yeah.
mean? First order means slope is 0. Second order differential means what, sir? I'm not able to understand that.
Second order differential means, okay, how, let's see how we could look at it, it geometrically. Okay. Okay, let me come back to that. I'll go to the slides and then we'll have some interpretation of that from that. We'll see if we can get something nice out of that. But for now, okay, just assume that we know these two conditions. The first one is a little easy to interpret because the slope goes to 0. Second one is a slightly, I think more not complex, but we will eventually try to understand that with by the geometry and of course the Taylor series expansion of that. I'll tell you that why that happens. Okay. But okay, so coming to that, so solving this is it's a possibly nonlinear equation, which might be difficult sometimes. Suppose I have an equation where I have x1 square plus twice x1 sine of x2 plus e power x3 times x4 equal to 0, something like this, right? These are usually not very easy to solve. Okay, and if they are not easy to solve, then we need to find that look at some other methods, typically numerical methods. And one of the famous algorithms in that direction is the gradient descent methods. So what does this do? Say, let's say I have I start with an example. F of xy is x square plus say 2y square. Okay, and I want to find the minimum of this function. Of course, by inspection, I can say that x equal to 0, y equal to 0 is the solution. Okay, but then I just want to understand the method, so it's easier for me to understand the method if I know if I start with a known example which I can intuitively do something. Okay, so what this method does is that we start with an initial guess. Okay. Start with the initial guess and then keep on doing some iterative steps. So I want to find, suppose I'm looking at say x of t. This will be x at t at 1, t minus 1 minus alpha times the gradient of f evaluated at t minus 1. So if I plot this function, it will be something like this. Okay, and then maybe I'm starting at some arbitrary point here, let's say 4,3. Okay, and then I want to search it in a way where it's along its gradient. So this will be the maximum descent it will go. So I start at this point, then I will maybe at the second iteration go to this point, third iteration might go to this point, and so on. So what also is required is that as I take my steps, I should get closer and closer to the origin, not at a linear scale, but at a good scale. So since I'm here, I can take first step to be like really large. Again, here I'm here, I can take the second step to be very large. Here I come, I just take the third step to be maybe a little smaller, and then a little smaller, and then until I converge at this point. So what I do is my iterative process gives me a series of points, start from here, and then keep going all the way till here. Okay. We'll also try to make sure that we don't kind of overshoot, or even if we overshoot, we just oscillate and settle to the minimum value. So what this method does is that while I am far away from the equilibrium, I take big steps. And while I'm closer to the equilibrium, I make small baby steps. I just slow down and say, look, this is where because my slope is getting closer to 0. I need to slow down a little bit to converge my search to a smaller point. Okay, so this is largely it. So in this case, I'm looking. So this is called as my learning rate. And of course, there are ways to see how we set this learning rate. But for this purpose, let us, for this problem, let me say that I start with an initial guess. I really have to start around this ticket. I cannot start somewhere here and start guessing, or somewhere here and start guessing. So my initial guess should satisfy the function. So let's say so any 0.4, 3 will give me some number. So this is my initial guess. I'll call this as x0. So the way this method works is, okay, I look at x1. This x1 is what? By this formula, x at 0 minus alpha, which is 0.1. What is the gradient of this function? The gradient of this function, gradient of x square plus 2y square is 2x and y. Sorry, 2x and 4y. Right? Because okay, this will be 2x, this will be okay. So this is my gradient. So what do I do is I compute the gradient at the t minus 1 time state, which means I'm looking at computing the gradient 2x 4y at the point 4, 3. Okay, what is my x0? X0, the initial guess is 4, 3 minus 0.1. Not a minus, but this is a dot here. 0.1 twice x is 8, and 3y 4 twice x is 8. 4 times 3 is 12. So I have 3.2 and 1.8. Is okay. So I start somewhere here. I end up somewhere closer to the. I'm not going away from that. So what this will ensure is that you are not diverging away from where you are supposed to go. Okay. Now I have x1. I compute x2. X at 2 is x at 1 minus 0.1, which is the learning rate. Again, I compute the gradient 2x 4y. Now at x at 1, which is 3.2 and 1,8. So what is it? This is 3.2, 1,8 minus 0.1. Twice of 3,2 is 6.4. This is 7.2, and I end up at some numbers which could be 3 minus 7, 2.56, 1.08, and so on. And then the next iteration will take me to 2.04, 0.64. The iteration after that will take me to 1.63.38, and then I keep on continuing until I go closer to the origin. So what we could also look at, so this the difference between these x's will so I'm taking large jumps at the initial points and then taking smaller steps as I go closer and closer. Okay, so few things here. Okay, who decides this alpha? Can alpha be 0.5? Possibly answer is yes, but it could happen that if you take a very large alpha, you might end up start here and then you go here and then you may your algorithm may not converge very fast, or it might just keep oscillating, or even some other things can happen. So, okay, how to choose a good alpha is something we will look at in the future lectures. But for now, what we could do is, so we can do this, and then when to stop the algorithm, we can say, okay, let my error be less than, say, some 0.001 and so on. Okay. Or the difference between these two equations can be maybe some very small number, say some 0.0. Closer. Okay, how to understand this in terms of the linear
Shobna,
regression
can you
problem?
please go on mute? Thank you.
Okay. Okay. So how do we understand this in terms of linear regression? So I'll just go with the example that we had started off with. My objective was to fit these 3 points. This was 0, 6. This was 1, 0, 2, 0, and the problem was fit a straight line. Of course, I know that there will be no one line which will go through these points, and I'm checking what is the closest of all these lines. Okay, so what is the closest y equal to mx plus c? In the first case, the equation would be, okay, y is 6, m is whatever, x is 0 plus c. Second was 0, y was 0, x was 1 plus c. Third is y was 0, x was 2 plus c. Okay. Now I'm solving for m and c. Right? This is what we did. We use the least squares and we use the QR decomposition and so on. But can I learn this as an optimization problem? Because each time what I wanted to do is to look at what is the closest line that fits into these 3 points. So the solution that we got the other day was, we had y was equal to -3x plus 5, which means when x was equal to 0, y was equal to 5, and then I had a line which was something like this. Right? When y was equal to 0, x was somewhere here. So this was the closest line. These were the errors. So the things in the red were the errors, right? And what these do is they minimize the square of each of these errors. Okay, so this is where we started off. Now suppose, okay, I may not be able to solve it some reasons using this method. So are there how does gradient descent help solve this? So suppose I know that m equal to -3. I'm writing this exam and then I just peep into my friend's paper and say, okay, he or she got an answer of -3. Okay, so I say, okay, I know now m, but what about c? Okay, so let us see what happens to okay, when c equal to 0, When c is 0, how does my solution look like? Y is minus 3x, which means it is a line which goes something negative slope of 3, maybe something like this. Okay. For each, then I will have some kind of an error. So there will be a error which use some slightly different color. So for this point, this will be the error. For 0.20, this will be the error. For this point, there will be some other error here. Okay. So at each point, I have the observed value and the predicted value. What is the predicted value? Predicted value is that for any given x, y satisfies minus 3 times x. Okay, let me look at the first point, which was 0,6. The observed value was 6. The predicted value was 0, right? Because y equal to 0, sorry, x equal to 0, y will also be equal to 0. Okay, then I look at what is the okay, I'll do it slightly better. Okay. So this is my point 0,6. This is my observed value. This is my predicted value. And then I'm looking at the sum of the error square. Okay, so observed value is 6, predicted value is 0. Sum of the errors is 36 because 6 observed minus predicted is the error, and that is 36. Okay, the second point is 1, 0. Observed value is 0. Predicted value, because okay, x equal to 1, y at x equal to 1, y will be equal to minus 3. So I have an error now of 0 minus minus 3. So the error square will be 9. Similarly, with 2, 0, observed value is 0. Predicted value is a negative of 6. And the error, which is 0 minus minus 6, is 36. So if I sum of the errors, this will be 36, and 36 is 72, and then a 9, and say this is 81. Okay, this is a lot of error. Let me say what happens when this is for c equal to 0. What happens when c equal to 1? C equal to 1, again the observed values will be 6, 0, 0. Predicted value would be, so now my model is y equal to minus 3x plus 1. So when x is 0, y will be equal to 1. The square is 25. Again, when x is 1, y is what? When x equal to 1, this is minus 3 plus 1 is minus 2. Error is of 4. Similarly, when y is 2, this will be minus 5. Error is 25. So when c equal to 1, the error is 25 and 25 to 50. It is 54. Okay, I can keep on doing this now. Let me say what will be the thing when c equal to 3. So I'm just, if I were to just plot this, plot c versus the error square. Okay, so I'll have a plot when I start with 88. I have next one was 54. I can do a c equal to 2. I might get something here, then I get something here, and so on, right? And maybe at some point of time I'll go, and then it might be have some pattern like this, right? So, and what I see is as c increases, my error is going down. I can quickly check that for c equal to 2 also and get into this. Okay, so I'm now searching for this point here. The search is on for this point. Okay, now I don't want to do this by trial and error. So I'll just see how does gradient descent help me. Okay, how does gradient descent help? It's a nice thing. So what is I have these 3 points 0, 6, 1, 0, 2, 0. And what I know is someone told me that -3 is a good slope, but I do not know this C. Okay, so what do I do is I look at, so I want to estimate this C, right? So I start with C 0. Let this be 0, right? As I started off over here. C equal to 0, I get some residue, but then at C equal to 1, I'm improving. So which is okay. Okay, so the gradient descent will say, okay, the C at 1 will be C at 0 minus some learning rate times the gradient of some function evaluated at C at 0. Okay, now how to determine this function? Okay, that will be the point of our okay, so can I write the, okay, so what does this is the equation I know, right? Y equal to minus 3x plus C. Okay. Now, what is the error? Can I write the error or the error square as a function of C? Okay, not bad. So should be possible. I can again look at the predicted value. Sorry, and write the observed value versus the predicted value. Predicted value is what I get from here. Okay, observed value. So I have a point called 0, 6. Observed is 6. Predicted here is minus 3x plus C. So the error will be 3 minus, so x is 0 here, 3, sorry. The error will be the observed minus the predicted. 3x plus C. What is x? X is 0. 6 minus C square. This will be the first point. Second point, 1, 0. Observed is 0. Predicted is minus 3 times 1 plus C. So this will be plus 3 minus C. So this will be 0 minus, so this will be 3 minus C square plus similarly the last term will give me for the point 2, 0. Observed is 0. Predicted is minus 3 times 2 plus C. So this minus this will give me 6 minus C whole square. Okay, so I have an error function now which is 6 minus C square plus 3 minus C square plus 6 minus C square. Okay, so now this is nice, right? This is a function I am looking for, which is a function which is the function of C, the error as a function of C. Okay, now can I compute the gradient of this function, which is the error? Well, that is nice. The gradient of this function would be, I take this is just one variable function. The first one will be minus 2, 6 minus C. Here will be again minus 2, 3 minus C, and minus 2, 6 minus C. So I do minus 2, 6 plus 3, 9. 9 plus 6 is 15 minus 3C, or this is a negative of 30 plus 6 times C. Okay, so this is my error function, or the gradient of the error function. Okay, so let us go here, right? So I'm again looking at this search method and say what is C of 1 given that C of 0 equal to 0. Let me fix my learning rate at 0.1 times the gradient of f at, now I'm evaluating this at C equal to 0. This will be minus 30. So this will give me C at 1 to be a value of 3. Okay, this is nice. From in one iteration, I jumped. I actually know here that my optimal value of C star equal to 5. Starting from C equal to 0, in one iteration, I just jumped to C equal to 3, which is not bad at all, right? I'm not doing like a linear search. I'm doing like because I'm far away. My first step will actually lead me take a big leap towards the optimal point. Okay, now
Sir,
Yeah. Yes, sir.
Yeah. So here the C1 you calculated. So what is the minus 30? I didn't get this one.
No, no, so
0.1
I'm just
into minus 30.
okay. So these are the errors, right, at each point.
Yeah, so that point, when you were calculating the C1 at the end, last step,
This one, this one.
no, sir, C1 equal to, yes,
30?
yes.
Okay.
Yes, yes.
This is okay. What is the formula? C1 is C0 here. What is C0? C0 is here. Learning rate is 0.1. And then I'm computing the gradient. So this is the gradient, right?
Yes, that's right.
The gradient of f at the previous point, which is C0. What's the gradient in general is minus 30 plus 60. When C equal to 0, it is minus 30.
Yeah, got it. Okay.
Okay,
Thank
now
you.
so now I'll do for the next iteration also. So C at the second iteration will be C at 1 minus 0.1. The gradient evaluated now again at C at 1. What is C at 1? This is 3. My learning rate is 0.1. Again, what was my gradient? This was minus 30 plus 6C. Now here I'm looking at what happens at C equal to 3. At C equal to 3, I get minus 12. Okay, so I do 3 plus 1.2. I'm at 4.2. Again, I do one more step. C of 3
So
is
C equal
now
to 1 and C equal to 3. And then the previous steps.
previous step, right? So C2 is C1 plus 0.1,
Yeah.
the gradient evaluated at C1. So this and this will be the same.
Correct. But I think we did wrong here.
We did wrong, huh?
Yes. We wrote
minus 24.
What is 24?
this minus 12. 3
Okay,
minus
this is-
0.1 into minus.
So,
C is equal to 3, no? Which was, sorry, C at the previous iteration. No, sorry, C at 1. Okay, sorry, let me do this again. Okay, I'm looking at C at 2, C at 1 minus 0.1, the gradient of f at, now I'm looking at the previous iteration, that is C at 3, I already, okay, so I'm at this point, right? I knew what is C of 1. Until this is correct, from 3 to 3.1. Then here C of 2 is C of 1 minus 0.1 with the gradient evaluated at C of 1. Okay, now what is C of 1? This is 3 minus 0.1. What is the gradient at C of 1 when C equal to 3? This is minus 12, right? Minus 30 plus 18 is minus 12. So 0.1 into minus 12. So this becomes 4.2.
Understood, sir.
This is okay?
Yeah, got it.
Then I have, okay, I just keep on doing this. C of 3 is C of 2 minus 0.1 gradient of f now evaluated at C equal to 4.2. I make another jump and I go to 4.68. I keep on making a little jumps, then I'll go to 4.87 and so on, right? In 5 or 6 steps, I'll go close to the desired point, which is C equal to 5. Okay, you can actually see, right, how we are slowly progressing in that direction. Okay, now I can do this also in a way that, okay, I have again these 3 points, 0, 6, 1, 0, 2, 0. Okay, 0, 6, 1, 0, 2, 0. Now, earlier I assumed that somebody gave me what is M, but this time I'm not lucky enough. So I just say, okay, now I have M and the C. So I know, so both are unknown now. Okay, in case both are unknown, how will I write my error function? So again, I start with the first point, which is 0, 6. What is my predicted one? Predicted is 6. Actual is mx plus c. So the residue of the error one will be 6 minus mx plus c square. Second point, I have 1, 0. Okay, so this will be, because x is 0, this will be 6 minus c whole square. Second point, 1, 0, the actual value is 0, predicted would be mx plus c. The error 2 would be 0 minus m is unknown, c is 1, sorry, x is 1 plus c square. So this will be minus, okay, this minus wouldn't matter. So this will be m plus c whole square. Okay. Third one, 2, 0. This is 0. Mx plus c. E3 will be 0 minus m times 2 now, because x is equal to 2, c, and then the whole square. So this will give me twice m plus c whole square. Okay, so what is my total error function? E is 6 minus c square plus m plus c square 2m plus c square. Okay, how will I solve this now? So how to get to the optimal m and the optimal c? How will we do this? Any guesses?
So here our function will become in two variables, m and
Exactly,
c.
right? Exactly. So I have a function now in terms of m and the
We
c.
can go to that equation, sir.
Which one?
In the previous equation, sir. Yes.
So, okay, so I'll have a function now in two variables, right? So now I want to minimize over m and c, f, m comma c. Okay, now I start with some initial guess, m0 and c0. Let that be, say, minus 2 and 0. Okay, then I will have m1, c1 will be m0, c0 minus alpha. The gradient of this function, gradient will be, the first function will be gradient with respect to c of e, and the gradient with respect, and we say call this m first and c first, gradient with respect to c, and then do this iteratively. Is that okay? Maybe you can just, for example, just try and do one round for just say what happens. This is my m0, c0. What is m1 and c1 for this?
Gradient will be calculated at m0 and c0.
Yes. So now I'll have two things. So just look at, okay, I'm assuming you So just look at this example before. Yeah, this is how we this had a function with the two variables.
So, sir, error function also needs to be differentiated for m and c respectively, right? And
Yeah,
then
yeah.
it will
So
form a vector.
yeah, just like here we had the gradient vector here, x square plus 2y square had a gradient vector of the form 2x and 4y. I will do the similar thing here.
Correct.
So
Okay.
maybe some of you can, maybe one of you can just try this for one iteration and tell me what is M1 and C1, starting from M1, which is -2, or C, which is 0, alpha of 0.1 and something here. I don't know if you just to get a little warmed up into this.
Sir, I got it as minus 0.8 and 0. I'm not sure whether it is correct or not.
Minus 0. Okay, I think one way to look at if you are going in the right direction is that the optimal answer we know is -3 and 5, right? So we should make some progress towards these two numbers. That would be the hint.
Mhm.
You got sir minus 0.8 and 0.4.
Okay, minus 0.8 and 0. Okay, keep trying this as a little exercise and see what could be the good initial guesses and what could be, maybe you may have to play around a little bit with this value. Maybe take this at 0.05 or something and see if we are converging to the right direction. Okay, so a little proof of okay, where we were. Okay, the second is so somebody asked a question earlier of why is it that the second order condition is a minimizer. Okay, so a little mathematical explanation to that is comes in the following way, that suppose if this is this and then this holds, then x star is a local minimizer. Okay, so again, this is just as I said earlier, this is just sufficient but not necessary. But we'll see what is the proof of that, right? So I have this since I'm assuming that this is true, that the Hessian at that equilibrium point is greater than 0, which means for a small point around that will also it will be greater than 0 because of continuity. And for any p which is not equal to 0, this will definitely be equal to 0. Okay. Now, if I go back to my Taylor series expansion of f around a small point along the equilibrium, this is 0. So I'm just left with these three things, right? Okay, which means that f at x plus tp minus f is greater than 0. Okay, so what is greater than 0? F at x plus tp minus f of x is greater than 0. And if this is greater than 0, the point which I'm looking at is a minimum. And for that minimum, the right-hand side becomes a positive number. And therefore, I get a local minimum. This is a little mathematical explanation to that. Okay, so I'll just stop here. I think this is good to stop today. Just we have learned a little bit of the gradient descent method, and next time we'll go to look at solving some kind of constraints optimization problem. That is where all our interest will lie in much of this course. For the unconstrained optimization, we'll just do the gradient descent method, and if we have time later, we'll also look at the stochastic gradient descent. Okay, good. So one of you can communicate with me, which with appropriate time for the session on for the quiz one. What I would like you to do is to ask specific questions related to the problems in the assignments, so that the discussion will be a little more fruitful and beneficial for both of us, because I would know what kind of problems you have attempted, how you have attempted, and if you're going wrong, how you're going wrong, and how we correct from that point of view.
Yeah, sure, sir. I'll let
Yeah.
you know.
Yeah.
Yes.
So, and then also just try some of these algorithms, or maybe we can leave this for the end sem later. For now, maybe we can focus a little bit on the upcoming quiz.
Sir, are calculators allowed in the exam?
Let me check. Maybe there'll be an online calculator, but I'll just check and let you know by the time we meet on. But there'll be some. You won't be handicapped. There'll be either an online calculator or you can have your own. One of these two will be allowed.
Okay. So
Yes,
do we get Python questions?
No, not in this. Not in this course.
Okay, no Python questions.
No. We'll just do things by hand and learn it.
Sir, I have few queries. First is, like Nandan sir have said that he will be discussing with you about the pattern of the exam, right? So is it finalized yet? Means it is going to be a MCQ or?
Yeah, it will be MCQ, MSQ, and short answer questions where you may have to compute something and punch in that number.
Okay. And since second, sir, we don't have slides of the current classes going on, right? So if you could please upload.
Okay. So of the optimization part or the other part? Before this one?
All before optimization as well, sir.
So I think
for the projection, I guess there are no slides. So from
okay,
where
so I
to
think you
refer
can.
to?
Okay. So I just straight lifted from the book on Gilbertstein. I think the linear algebra and applications by Gilbertstein. That is, I think the copy is available online. You can download it easily.
Yeah,
So
that is already available. Yes.
That's all. I think I'm just doing exactly from that.
Okay.
Yeah.
One more thing, sir. Could you suggest some book for this optimization and beyond, right? Like beyond the point, like we have done with the linear algebra, right? So you have suggested Gilbertstein for that. What is for further syllabus?
Optimization. Let me tell you by next week, because there's no one book which I'll follow. I'll keep giving notes, and then I'll suggest one book. Let me think of that and give you one book. But I'll give
Sure,
you
sir.
slides
Thank
and
you.
notes as and when needed.
Sir, both the assignment submission date. So you're saying after next discussion, we'll be submitting both the assignment. Is that correct, sir?
No, the assignment, I think the date is extended till 8, right? So please submit first assignment by 8th.
8th, okay. And the second one, after post-exam, we can submit, right?
We'll see what is the date. We'll work on that. Let exam get over next Monday. We'll see what is a good date for that.
Okay.
Yeah. Okay.
Okay, thank you.
Okay. I'll let you take a little break before the other class. So I'll see you again sometime later this week.
Sure, sir. Thank you.
Okay. Yeah. Okay. And it'll also be nice if you can just give me a questionnaire so that we can directly go to the questions and quickly answer those.
Mhm. Okay.
Okay. Thanks.
Thank you, sir.
Thank you, sir.